Now I'm going to start to talk about the distributed load in the three dimension. We previously discussed how we will deal with the distribution, with distributed load in 2D. So let's look at um, what it was at the 2D dimension. So if we have, for example, a beam like that, and then we had a distributed load on that beam, similar to that. It's a simple distributed load. Um, if we had something like that, and then it was the length of that load was assumed was L, and the distributed load magnitude was W in Newton per meter. If you had something like that, and then we wanted to do the calculation, what we would say is that this distributed load, we wanted to find the resultant force. The resultant force was Fr. So we want to find its magnitude and its location. So we know that the resultant force, the Fr, was the area of that distributed load. So it was L times W. So it was L times W, and it was basically the area of the load. So it was the area of the distributed load. So that was how we calculated the uh, uh, what it says that the magnitude of that, and the location of that load. If we wanted to find the location of that load, if the location of that load was located as X, the location of that load was at the centroid of that area. So it was the half of L, or it was at the um, centroid of load area. But that was how we will find the distributed load in 2D. It's going to be very similar if you are thinking of that in 3D dimension. So if I go ahead and um, do the same thing in 3D, so assume I have a plate, and on that plate I have a distributed load. So assume I have a plate like that, and then there is a distributed load on that um, plate. So it's going to be distributed load on that plate. So we have a distributed load on the plate, something like that. So when we're talking about the distributed load, so what in 3D, a distributed load on the surface, what we can say that is probably one thing can um, mention is the air pressure. So the air pressure applied on any surface that you have, on every point of the surface, you have that air pressure. Similarly, like what we have for the water pressure, if we have the object is under the water, uh, then in that case the water pressure applied on every point of that surface, so you have the distributed load on that surface, and how we'll deal with that. So similar to what we have in the 2D, we have the resultant force from that distributed force, and we want to find it. Similar to 2D, in the 2D what we have, it was the Fr was the area of the load. Similar to that, in the 3D, the Fr is the volume of the load. The so the magnitude of the resultant force in 2D is the area of the load. In 3D is the volume of that load. So that volume, you calculate that volume. Whatever the value is the value of that uh, resultant force, the magnitude of the resultant force, and then it's gonna apply it at some x and y. So it's gonna apply it at some x and y, and then the x and y is at the centroid of, here is was the centroid of the load area. So the load create an area, and the resultant force was at the center of that area. Similar to here, you have the load created volume, and that resultant force would be at that centroid of that volume. So it's going to be is at centroid of load volume. So you find the centroid of that volume, and wherever is that centroid is where that resultant force would be active. Uh, one other point that we usually need to know about when we are dealing with the distributed load is that if I have a plane and assume I have distributed load on that. If the distributed load is only changing in one dimension as is constant in the other dimension, then we can convert it into 2D form. So for example, here assume that in the L, this one is going to be the L, and this one is going to be B. Assume that the distributed load is going to be changing along the L, but it's not changing along the B. So for example, it just starts from here and then increases to some values here. So you have something like that. So it starts but increases. The same here, it starts with the same value here and increasing it to the same value to that end. But along the B is going to stay constant. It's not changing along the B. So if you go along the B, it will stay constant. In that case, we will change this to 2D. So assume this one here is W1 as the Newton per square meter, and here at this end it becomes W2, and again is a Newton per square meter. Now when we want to convert it to 2D, because it's not changing it in the width, we'll consider it as so this length. So it's going to be the L, so the length of the L. So we will only consider this edge, and then we put the load on that. We put the whole load on from that surface, from that plate on that edge. So how we would do that? So the shape is going to be the same, shape of the load, but the magnitude is going to be different. So when we do the calculation, this one is going to be W1 times B. So basically we just multiply it by the width, and it's going to be Newton per meter. And this, the same here, is going to be W2 times B, and the same is going to be Newton per meter. So we would have something like that, and so it's going to be in the 2D format. And then when we have it in 2D format, we can do the calculation and find the resultant force on these 2D ones, which is going to be something sitting here as a resultant force. So what we have done here is basically we times the front face, whatever we have on the front face, by the width, because there's nothing changing in the width. If we times the front face by the width, it's basically that volume that we compress that volume to that front face by times it the front face by the B. So every load we have in the front face, we times it by the B, and then it will becomes a 2D condition like that, and then like before we can solve it as a 2D problem, and we get all the calculation we have. So it's basically that's how we go from the 3D load to 2D load uh, if you have the load only changing on one side and doesn't changing on the other side, so we can do that. If it doesn't changing on both sides, also we can do the same things. We just choose one of the edges and then times it by the width and bring everything on one edge, make it 2D, and then do the calculation.